Hey everyone, I figured I'd start doing some videos about what I think is interesting and use my social media more efficiently as opposed to not at all. Um, I want to explain how beta decay works and why the weak nuclear force is considered weak and why its interactions take a ridiculous set of circumstances in order to actually play out, and why different particles or different atoms, isotopes have different half-lives, and this kind of stuff. So I think it's amazing. It's literally the wonders of the Lord, and I think people take for granted how fucking nuts the world around us is. It's just mind blowing. Like, it's just so insane. This is why I think it's interesting. I just think it's fucking awesome. But for those of you who don't know, beta decay is when a neutron in an atomic nucleus decays into we measure an electron emission. But what happens is the neutron actually decays into a proton and then a W boson, which is the one of the force-carrying particles for the weak nuclear force. There's the plus and minus W bosons, which are charged, and then the Z boson, which is a neutral particle. So it does not carry an electric charge. However, these particles are massive. Talking the W boson has a natural rest mass of 80 billion electron volts, give or take. And what's required for beta decay, for example, in the case of carbon-14, which is what they use for radiocarbon dating, is about 156,000 electron volts. So what does that actually mean? So like I said, the neutron will decay into a proton and a W boson, and then the W boson, on a very short time frame, will decay into a electron and then a neutrino. And this boson needs to be a very low mass compared to what it normally is. So generally, an atomic nucleus will become more stable with neutrons, as is in the case of uranium. For example, uranium-238 has got 92 protons and then 146 neutrons. It's got a half-life of about 4.5 billion years. That's the age of the Earth, according to our measurements. And uranium-235 has got 143 neutrons in addition to its 92 protons. Uranium-233 has got 141, and these particles have half-lives. 235 has got about 700 million year half-life, and then as you drop it, 2 neutrons, its half-life drops so significantly down to 159,000 years. So that is a major drop. But what you have to keep in mind is that there are exceptions to this rule, because the atomic nucleus is actually arranged in shells. Protons and neutrons are arranged in shells. These are actually waves, more or less, on a fundamental level. And so the atomic nucleus as a single unit, as a structure, has its own wave function, which is inclusive of all the protons and neutrons in the nucleus. So it's sort of like the electron orbitals in an atom, generally speaking, in that regard. And so here's an example of neutrons not actually helping in terms of stability of the nucleus. Uranium-236 has got those 92 protons. It's got 144 neutrons, and it's got a half-life of 234 million years. That's 10 to the 7th power. And notice, uranium-235 is one less neutron, and it's got a longer half-life than uranium-236. I'm sorry, that's 20 million years. That's 10 to the 7th power. And this is 10 to the 8th power. So my mistake, but still, even more so. And so this depends on the placement of the protons and neutrons in, higher and lower energy levels in the atomic nucleus, and and the binding energy of the nucleus, and so on and so on. So there's a lot of nuance that goes into this stuff. But in the case of, for example, carbon-14 will decay by beta decay into I forget. But what happens is one of the neutrons in the nucleus will decay into a proton, like I said, with that double boson, and then the electron is what we measure. The neutrino is likely to pass through every piece of matter it encounters and then fly off into the void of space for the rest of eternity. By the way, neutrons are so unlikely to interact with anything, it's impressive. A neutrino is so unlikely to interact with anything that it is, on average, it will penetrate a light year thick of lead before interacting with the particles. So that is how unlikely we're talking about for these interactions to occur. Now, here you go. We need a W boson with a mass of 156,000 electron volts, as opposed to its normal mass of about 80 billion. So it's actually got a range of masses here, and that's due to the Heisenberg uncertainty principle. As we discussed, all of this stuff occurs in a very short time scale. So what happens is the particle itself, as a result of its wave-like properties of quantum mechanics, it has certain probabilities of being certain masses. So the most likely mass for us to find a W boson is a measurement of about 80 billion electron volts, 80 giga electron volts. It's got a mass, it's between 79.5 and 84.5 billion electron volts, with about a 90% probability. And then as you go far enough to the left, you get 70 billion electron volts. You'll have about 1% probability of measuring a W boson at that energy, and so on and so on. So the likelihood of finding a W boson with 156,000 electron volts is so ridiculously low that it's nuts. It's essentially, that's the reason that that standard nuclei we encounter every day don't just literally explode right away. If the weak nuclear force was stronger than it is now, then larger atomic structures like nuclei would not even form in the first place, because there would be likely to decay immediately after formation. Essentially, the particles that make up the neutron are going to be more likely to exist in the universe than the neutron itself, even in systems with bound together like in an atomic nucleus. And so the reason why we're able to actually have a beta decay and that actually results in a functioning universe, and this is one of the reasons that it's just so ridiculous to even claim that that this universe is not intelligently designed. This is just, there's way more. I can keep going. There's no shortage of evidence that that God created everything. And so in any case, we're able to find a beta decay because, like I said, this type of stuff happens on very short time scales. These particles are extremely unstable, and they tend not to form. And when, for example, a W boson will show up, in the system of a neutron, then it is unlikely to, but still possible on a very low likelihood, that it will exist for a short while at a mass such as 156,000 electron volts, and then it will decay into a electron and a neutrino, and then we call that beta decay. So because it's such a short time frame, we are able to measure its energy is much more variable, because on interactions like this, the uncertainty principle is very important. And so, for example, as the time frame that this interaction occurs tends to become smaller, the variation in energy of the particles involved is much larger, and so we get a potential for the particles to occupy a much larger range on a practical level, hence the existence of beta decay, than just a longer scale interaction. And this is also lends to the fact that the position and momentum of a particle is also dependent on one another, and so we can see particles that are supposed to be extremely massive occupy quantum states that seemingly contradict the standard measurement that we would expect according to the standard model, and then we get radioactive bananas, we get radiocarbon dating, we get uranium actually decays by alpha decay. Pretty sure every isotope of uranium decays by alpha decay. That's just to make the point that even though the tendency is for neutrons to add stability, sometimes they can actually screw with the stability of the nucleus. And the neutron itself, if it was not in a system of very high energy and pressure like in an atomic nucleus, it actually would decay much quicker than if it was in a nucleus, and for that reason also, it takes much more time for a weak interaction to occur in an atomic nucleus as opposed to a free neutron. And so this stuff is amazing. I just think it's awesome. And hope everyone has a great day.